Welcome to our quantum deep dive.
So let's start with a wild thought. What if, for every single particle that makes up you, me, and everything we see, there was a perfect opposite? A mirror image of our reality, built from stuff that's identical to ours, but with all its properties flipped.
And no, this isn't science fiction. It's the very real, very strange world of antimatter. And to guide us through this whole mirror universe idea today, we're going to be drawing from an incredible essay by Georg O. Schneppat. It's really going to help us unpack what this is all about.
All right, so here's the plan. First, we'll get into the whole idea of this mirror universe and its anti-building blocks. Then we'll see how scientists are actually making this stuff in labs to answer some of the biggest questions about the cosmos. And finally, we'll look at some mind-blowing future tech this research might just make possible. So, where did a crazy idea like this even come from? You might guess it started in some high-tech lab or with a powerful telescope. But nope. The story of antimatter actually begins on a piece of paper with a single, elegant, and kind of puzzling equation. Back in 1928, the physicist Paul Dirac came up with this equation to describe the electron, but it had a surprise hidden inside. It actually had two solutions. One was the good old electron we all know and love, but the other, well, it described a particle that was identical in every single way except it had a positive charge. It was the electron's perfect opposite. Now, at first, the second solution just looked like a bug in the math. I mean, particles with negative energy? It sounded impossible, totally nonsensical. But Dirac, he made this brilliant leap of faith. He suggested this wasn't an error at all, but a prediction of an entirely new kind of matter, antimatter. And what started as theory very quickly became reality. Just a few years later, in 1932, this positron, the anti-electron, was actually found in cosmic rays. Then, fast forward to 1955, and the antiproton was discovered. And this was huge because it proved that this whole mirror image rule didn't just apply to tiny light particles. It applied to the heavy hitters too, the hadrons that build our world. Okay, so we just mentioned antiprotons, which are a kind of anti-hadron. But hang on, what even is a hadron? To really get a handle on antimatter's building blocks, we've got to first understand our own. Simply put, a hadron is basically any particle that's made of quarks. These quarks are fundamental particles, and they're kind of glued together by what's called the strong nuclear force. The protons and neutrons inside every single atom, yep, those are hadrons. They are the real heavyweights of the subatomic world. And these hadrons come in two main flavors. You've got baryons, like our protons and neutrons, which are made of 3 quarks. But then you have mesons. These are really exotic particles made of 1 quark and 1 antiquark bound together. This right here shows you just how deeply matter and antimatter are connected. And here's that mirror image in action. Check this out. A proton is made of 2 up quarks and 1 down quark. So its perfect opposite, the antiproton, is made of 2 anti-up and 1 anti-down antiquarks. This simple flip is enough to reverse its charge from +1 to -1, and it flips another weird property called its baryon number, which is basically just a counter for these heavy particles, from +1 to -1. And this whole opposition thing, it follows 3 really simple but profound rules. First, they have the exact same mass, identical. Second, their charge is perfectly opposite. And third, and this is the most dramatic one, if a particle ever meets its antiparticle, they don't just collide, they annihilate. They literally vanish in a flash of pure energy. And it's all perfectly described by Einstein's famous equation, E = mc². Okay, so that brings up a really big question. If this antimatter stuff annihilates the second it touches regular matter, how in the world do scientists create it, let alone study it? Well, the answer involves some of the most incredible machines humans have ever built. At a place like CERN, the recipe is pretty much just pure power. They take a beam of protons, get them going at nearly the speed of light, and then slam them into a metal target. The energy from that collision is so intense, it literally converts into mass, creating a spray of new particle-antiparticle pairs. From all that debris, powerful magnets then sift out the antiprotons, slow them way, way down, and get them ready for capture. So how do you trap something that you can't let touch anything? You build a magnetic bottle. That's basically what a penning trap is. It uses a super strong magnetic field to force the antiprotons to fly in a little circle, and then a weaker electric field to keep them from escaping out the ends. The antiproton is just held there, floating in the middle, touching absolutely nothing. And to make these traps actually work, the conditions have to be unbelievably extreme. We're talking about a vacuum that's emptier than deep space, in temperatures cooled to nearly absolute zero. This is all to stop any stray atoms from wandering in and causing an annihilation, and it also slows the antiprotons down enough so we can actually study them precisely. Okay, so we can make these little antiparticles in a lab. Awesome. But why? Why go through all this trouble? Well, it turns out these tiny anti-hadrons might just hold the answers to some of the biggest, most fundamental questions we have about the entire cosmos. And it all comes down to maybe the single biggest mystery in all of physics, the baryon asymmetry problem. See, all of our theories about the Big Bang say it should have created matter and antimatter in perfectly equal amounts. But if that happened, they would have all just annihilated each other, right? We'd be left with a universe of nothing but light. But we exist. The stars and galaxies exist. So the question is, where did all the antimatter go? The best theory we have right now is that there was a tiny, tiny imbalance. For every billion matter-antimatter pairs that were created and destroyed, just one extra particle of matter somehow survived. Think about that. That tiny cosmic rounding error, that 1 in a billion survivor, is the reason everything we see is here today. Every star, every planet, and all of us. So the hunt for this missing antimatter is on, and it's happening everywhere. Up on the International Space Station, experiments are searching for things like stray anti-helium, which would be a sign of entire anti-stars out there. Telescopes are scanning the skies for the gamma-ray flashes you'd expect to see if a galaxy and an anti-galaxy collided. And back on Earth, at CERN, they're asking an even crazier question. Right, we just assume gravity pulls on everything. But what if it doesn't? What if antimatter falls up? It sounds bonkers, but experiments like AGIS and GBAR are actually trying to answer this. They're creating anti-hydrogen and just watching to see which way it falls. I mean, if it goes up, our entire understanding of the universe gets turned on its head. But this whole quest to understand anti-hadrons isn't just about looking back to the beginning of time. It's also pushing us towards a whole new frontier of technology, with some really mind-bending applications on the horizon. Since matter and antimatter are supposed to be these perfect mirror images, comparing them gives us the ultimate reference point. If we can precisely measure the energy levels in a regular old hydrogen atom and compare them to an anti-hydrogen atom, we could create clocks and other measurement tools that are thousands, maybe millions of times more accurate than anything we have today. And that same incredible sensitivity could lead to totally new kinds of sensors. A single trapped antiproton is like a perfect compass needle, right? It reacts to the tiniest, faintest magnetic or electric fields around it. You could imagine this leading to new medical scanners or material sensors that can detect things far too subtle for our current technology. This all ties into a really core idea in physics called CPT symmetry. It basically says that if you take a particle and you flip its charge, that's the C, flip its orientation like a mirror, that's parity, or P, and then reverse the flow of time, the T, the laws of physics should stay exactly the same. So experiments are testing this by comparing protons and antiprotons with insane precision. If they find any difference, no matter how small, it could point to a whole new layer of physics we don't even know about. And thinking about all these quantum properties opens up a really futuristic possibility: quantum computing. A quantum computer uses qubits, which can be in multiple states at the same time. So what if the quantum spin of a single trapped antiproton, its up or down state, could be used as one of those qubits? Now, the challenges here are, well, they're enormous. You'd need a perfect vacuum, obviously, to stop it from being annihilated. The quantum state itself would be super fragile and easy to mess up. That's a problem called decoherence. And just controlling a single anti-hadron with that much precision is right at the bleeding edge of what's possible today. It's a long shot for sure, but it's a pretty tantalizing vision for the future of computing. Wow. Okay, so we've gone from a strange little solution in a 1928 equation to these giant machines forging matter's opposite, all the way to the deepest mysteries of the universe and the far, far future of technology. When you get right down to it, anti-hadrons are so much more than just exotic particles. They're the universe holding a mirror up to itself. And by studying that reflection, we're not just learning about antimatter. We're learning about the fundamental rules that govern our own reality, and the very reason that we exist at all. Which really leaves us with one last big question. We assume that the mirror between matter and antimatter is perfect, but what if it's not? What if there's a tiny flaw, a little crack in the reflection? That imperfection could be the very reason we have a universe in the first place, and it could be the key that unlocks a whole new era of physics.
Thanks so much for joining us for this explainer, which was based on the fantastic work of Jörg Ois Schneppat.
To learn more, you can visit schneppat.de. Until next time, stay curious.
Schneppat.de is a private project by Jörg Ois Schneppat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.